Hello viewers, you are welcome to another edition of our lesson in physics. In our last lesson, we looked at scalar quantities and vector quantities. After examining the difference between the two types of quantities, we defined some important scalar and vector quantities, and thereafter concentrated on vector quantities. We looked at the negative of a vector, equal vectors, and the scalar multiple of a vector. We looked at momentum and impulse as scalar multiples of vectors and identified them as vectors too. In this lesson, we are going to look at addition of vectors. We shall consider the triangle law for the addition of two vectors and the polygon law of vector addition in general. We shall also look at the resultant of vectors and the result of the addition of vectors. We shall also look at the addition of two vectors, how it is done using the triangle law of vector addition, and how the parallelogram law can be deduced from this. We shall, after this, look at the resolution of vectors into components and briefly look at how the resolution of two or more vectors can be used to determine their resultant, leaving the actual work of determination of resultant for the next lesson. By the end of this lesson, therefore, you should be able to 1. Add two vectors. 2. State the triangle and polygon laws of vector addition. 3. Use the triangle law of vector addition to obtain the resultant of two vectors. 4. Show that vector addition is commutative. 5. Deduce the parallelogram law of vector addition. And 6. Resolve a vector and express it in components. We would begin by looking at addition of vectors. That is the resultant of vectors. Suppose two vectors A and B are shown on the screen. For convenience, we may take vector A and vector B as forces. Suppose we want to add the two vectors, which amounts to obtaining the sum of their effect taken together. Then we are said to be determining the resultant of the vectors. We shall first assume that the vectors are free vectors, so that they can be slid while maintaining their directions. In some cases, vectors may be treated as free, bound, or localized, so that they may not be moved from where they act, especially when they act on a given body. To add vector A and B, we place the second vector B so that it begins where the first vector A ends, as shown on the screen. The arrows will therefore flow from A to B. Thus, A starts from O and ends at A, and vector B starts at the end A of vector A and ends at B. it can be seen that to go from O to A and then from A to B amounts to starting at O and ending at B, which can be achieved using one direct and straight path, OB, as shown on the screen. Thus, the resultant of a vector A and a vector B is the vector C, represented by OB and indicated by double arrows. The resultant will always be represented by double arrows. Thus, we have vector A plus vector B equals vector C. That is, C is a resultant of vector A and vector B. In your mathematics lesson, you could have A plus B equals C, written as OA plus AB equals OB, where OA equals A, AB equals B, and OB equals C. We would now want to consider the triangle law of vector addition. An important concept comes out. Two vectors, vector A and vector B, and their resultant vector C, form a closed triangle. This also means that if two vectors have a resultant, vector C, and vector A and vector B are represented by the adjacent sides of a triangle, then vector C will be the closing side of the triangle. This is the triangle law of vector addition. Thus, the addition of two vectors follows the triangle law of vector addition. In general, if any number of vectors are added, the vectors and their resultant will form a closed polygon. This is the polygon law of vector addition. Suppose 5 vectors, vector A, B, C, D, and E, have a resultant F. We can show them in a polygon to illustrate the general law or polygon law as shown on the screen. Note that if A starts at O and E ends at E, then the resultant F is the vector OE starting at O and ending at E. In your mathematics lesson, you could have F equals OA plus AB plus BC plus CD plus DE, implying F equals vector A plus vector B plus vector C plus vector D plus vector E. Let's now consider the commutative law of vector addition. Suppose two vectors A and B act at a point O as shown on the screen, and we want their resultant C. Since we want the resultant of vector A and vector B, we may keep A where it is and slide vector B, maintaining its direction, so that its starting point comes to where vector A ends. as shown on the screen. When this is done, the resultant C of A and B can be shown as in the diagram, that is A plus B equals C. On the other hand, since the resultant of vector A and vector B represent the sum of their effects, that is, the combined effect of vector A and vector B, we may also keep B where it is and slide vector A, maintaining its direction, so that the starting point of vector A coincides with the end of vector B as shown on the screen. This approach gives the resultant C of A and B. That is, B plus A equals C. We may put diagrams into combined diagrams as shown. This illustrates the fact that A plus B equals C, B plus A equals C, implying A plus B equals B plus A equals C, which is a statement of the commutative law of vector addition. We would now want to consider the parallelogram law of vector addition. It is seen that the application of the triangle law of vector addition leads to a situation in which vector A and vector B and their resultant C may be represented in a parallelogram OABC. The geometry of the diagram shows that the two vectors A and B acting at a point O and represented as adjacent sides of the parallelogram have a resultant C, which is the diagonal of the parallelogram drawn from the point O. This is a general law called the principle of parallelogram of forces, which in actual fact is applicable to all vectors and not to forces alone. In effect, it is the principle of parallelograms of vectors and not of forces alone. The principle is formally stated as: if two vectors acting at a point are represented in magnitude and in direction by the adjacent sides of a parallelogram, then the resultant of the vectors is represented in magnitude and in direction by the diagonal of the parallelogram drawn from the point. I would want you to make a sketch of the possible cases in which two vectors act at a point and use the parallelogram law to sketch their resultant. Two cases are shown on the screen. Let's now consider resolution of vectors. It is often necessary to find the effect of a vector in a given direction. Suppose a bag of cement or a cement block is placed on the floor and a rope is attached to one end of it so that it can be pulled by a force F, which becomes tension in the rope. Suppose F makes an angle theta with the horizontal as indicated on your screen. It may be required to find the effect of force in the horizontal direction. Example, in the direction in which B moves when pulled by F. Let us call this direction the X direction. It may also be required to find the effect of F in the vertical direction. Let us call this direction the Y direction. This may be represented as shown on the screen. If we are finding the effect of F in the X direction, we say we are resolving F in the X direction. If we are finding the effect of F in the Y direction, we say we are resolving F in the Y direction. We may also say that we are determining the components of Fx and Fy, of F in the horizontal, that is X direction, and vertical, that is Y direction respectively. Even though vectors may be resolved in any direction, they are usually resolved in two orthogonal or perpendicular directions. That is, we resolve F into two orthogonal components, Fx and Fy. If a force F is applied to B, the effect of Fx is to pull it in the direction OX, as shown by the arrow. And the effect of Fy is to lift B in the direction OY. Now let us attempt to determine Fx and Fy in terms of F and theta. For convenience, we can obtain a right-angled triangle which can be used for the analysis. Now you have learnt about the three trigonometrical ratios: sine, cosine, and tangent of an angle. If you have forgotten, we can do a quick revision, since the first two of them will be useful here. Do you remember the mnemonic so, ka, toi? So means sine equals opposite O divided by hypotenuse H. That is so. Ka means cosine equals adjacent A divided by hypotenuse H. That is ka. And toi means tangent equals opposite, that is O divided by adjacent A, that is toi. Can we now apply them? We shall shorten sine, cosine, and tangent to sine, cos, and tan respectively. From the diagram we saw on the screen, cos theta equals OA divided by OB. That equals Fx over F. That implies Fx equals F cos theta. Let's represent this by I. Again, sin theta equals AB divided by OB. This equals Fy divided by F. This implies Fy equals F sin theta. Let's represent this by II, where Fx, Fy, and F are magnitudes of Fx, Fy, and F. Note that if you are to do resolution effectively, then 1. and 2 must be at your fingertips. You should be able to write them out fast without the derivation done here. Remember that the adjacent fx equals hypotenuse times cos theta, and opposite fy equals hypotenuse times sine theta, where, for example, adjacent means side adjacent to the angle theta in question, as shown on the screen. Thus, the component of f are f cos theta equals fx and f sine theta equals fy in the horizontal and vertical directions respectively. F can thus be represented as f equals, into big brackets, written in a vector form, fx fy equals, into big brackets, f cos theta f sine theta, written in a vector form. Or simply, f is expressed in components as f equals big brackets f cos theta f sine theta in vector form. Note that when we write in components, we write fx first before we write fy down. That is, in looking for the combined effect of the two components, we move first along the x-axis before moving along the y-axis. Because when the two components fx and fy are added, we get vector f. One may say that resolution looks like the reverse of the addition of two vectors, but not the addition of vectors in general, since we normally resolve two components, but any number of vectors may be added. Let's consider this question. Express f in components if f equals 10 newtons and theta equals 60 degrees. The answer is shown on the screen. F equals 10 cos 60 degrees and 10 sine 60 degrees. This equals 10 times 0.5, 10 times 0.866. This equals 8.66. Resolution splits a vector into two components, but addition of two vectors brings them together. That is because resolution splits a vector into components. Representation of vectors by resolution and subsequently representing them in components may be referred to as composition of vectors. Let's consider this question. Represent in components the following forces which act at a point O. I would want to give you a hint on how to go about this question. For each vector, get the components by first moving from O along the x-axis, and then from there along the y-axis. If we move to the right along the x-axis, the component is given a positive sign. Otherwise, we have a negative sign. If we move vertically upward along the y-axis, the component is given a positive sign. Otherwise, we attach a negative sign. Now, let's proceed. F1 equals F1 cos theta 1, F1 sin theta 1. F2 equals negative F2 cos theta 2 and F2 sin theta 2. F3 equals negative F3 cos theta 3 and negative F3 sin theta 3. F4 equals F4 cos theta 4 and negative F4 sin theta 4. Let's consider question 2. Express the resultant F of the four forces in components. The solution would be F equals F1 plus F2 plus F3 plus F4. This will be equal to F1 cos theta 1 and F1 sin theta 1 plus negative F2 cos theta 2 and F2 sin theta 2 plus negative F3 cos theta 3 and negative F3 sin theta 3 plus F4 cos theta 4 and negative F4 sin theta 4. F equals F1 cos theta 1 minus F2 cos theta 2 minus F3 cos theta 3 plus F4 cos theta 4. And F1 sin theta 1 plus F2 sin theta 2 minus F3 sin theta 3 minus F4 sin theta 4. In the next lesson, we shall be going into the actual determination of the resultant with particular examples in which the forces and the angles are known, so that we can proceed beyond what we have done here. I'd want you to write down these questions and practice them. 1. What do you get when you add two vectors? 2. What are the following? A. Triangle law. B. Polygon law of vector addition. 3. Express the following forces in components. This lesson has been interesting, hasn't it? This is where we end today's lesson. Till we meet for the next lesson, it's goodbye.